Welcome back. So I don't know what day it is that you're going to be watching this video, but for me today is St. Patrick's Day, so happy St. Patrick's Day. We're going to have lecture number 18 today, Simple Harmonic Motion and Elasticity, continued. So we started it last time, we're going to continue it today. We're going to look at a motion, first of all, that looks like simple harmonic motion. Certainly on the surface it does, but we'll see that it actually isn't. But under a certain approximation, we can approximate it as simple harmonic motion. And that is the motion of what we'll call a simple pendulum. Now, a simple pendulum is basically just a point mass, a small mass, on the end of a rod. Sometimes it's described as a rigid rod or a string. The important point is that it's not going to be bending or anything like that. We're going to maintain a constant distance from the point mass to the point of support. If we then displace it and allow it to oscillate on its own, this certainly looks like simple harmonic motion. It's going back and forth, and we could imagine plotting this motion as a function of time, and it certainly looks like it would be something very close to a sine wave. Well, what we're going to do is we're going to analyze this motion and see really what sort of motion it has, or at least approximately. Now, because it's actually moving along a section of an arc, a section of a circle, we're going to analyze this using rotational motion rather than translational motion in x and y. The x and y motion of this would be much more difficult because it's moving both in x, say, and in y as it goes up and down. So it's going to be a whole lot easier to analyze this using rotational coordinates. So let's draw a free body diagram for the mass and see what it looks like. Okay, so here we go. Here's our free body diagram. We've got our mass swinging on the pendulum back and forth like this. And let's imagine we're going to look at it at some instant when the mass forms some angle theta relative to the vertical. Now, the mass is suspended from some point up here that's attached to some fixed surface up here, like the ceiling or something like that. And let's choose our origin up here at this point. The mass is moving along a circular arc like this, and that circular arc is going to be centered at that point, the origin, the point of suspension, so that looks like a good point, a good place for us to put the origin. Now let's assume that our pendulum has some length L, so our mass M down here is going to maintain a constant distance L from the origin. The forces acting on the mass are the weight. So if we've got a mass mg, the weight will be if we have a mass m, the weight will be mg. It's going to be acting straight down. And then the tension from the string. So as the mass oscillates back and forth, the string is going to be pulling on the mass, and we know tension is always along the direction of the string. So the tension from the string is going to be acting on the mass, pulling it back up towards the origin. Okay, now, like we said before, we're going to look at this in terms of the rotational quantities. We're not going to analyze this using x and y. We'll analyze this using our angular rotation quantities. So, what is the torque acting on the mass? Well, we've got two forces, so let's figure out two values for the torque. Remember, torque is equal to Rf sine theta. Now I do apologize for using the same angle here. Remember, theta in this equation means the angle between R and F. So let's figure out what are the torques due to our two forces, the tension and the weight. So first of all, what is R? Remember, R is the length of the vector R, and the vector R goes from the origin to the point where the force is applied. Now the forces, both forces, are applied at the location of the mass. So R is a vector that will go from the origin right down along the string to the mass. Okay, so for the tension, let's think about that. Well, what's the angle for the tension? What is theta for the tension, the angle between R and F? Well, R is this way, F, the tension is that way, putting them tail to tail. What's the angle between them? 180 degrees. What is sine of 180? 0. So the tension gives 0 torque to the mass. Okay, so we can ignore the tension in terms of our torques. Now, what about the weight? Well, for the weight, what is R? R is the distance from the origin to the point where the force is applied, which in this case is L, times the force, and the force is mg, times sine of theta, theta being the angle between R and F. Well, if this is R and this is F, bring them tail to tail, so we can extend R in that direction. That would be the angle, but that is exactly the angle theta that we set up here. So this theta for the weight is actually whatever this positional angle theta is here. So we have that the torque is L mg sine theta. Now, what's the direction of the torque in this case? Well, the torque is going to tend to rotate the mass back in this direction. In other words, in a clockwise direction. And remember, we will typically choose our orientation so that counterclockwise is in the positive direction. So clockwise would be negative. So this is actually going to be a negative torque. So we have the torque acting on the mass, due to the weight, in this case, that's the only torque, is going to be minus L mg sine theta. Now, we can look at this and see, is this going to be simple harmonic motion or not? Well, remember when we looked at the mass on the spring, we got simple harmonic motion when we had a restoring force that looked like F equals minus kx. In other words, the force, the restoring force, we know it's a restoring force because of that negative sign. The force was always opposite the displacement. Well, what do we have in this case? Well, we have a restoring torque, and we know it's a restoring torque, again, because of that negative sign. The torque is always going to be in the opposite direction of the displacement. If theta is positive, in the positive direction, the torque is negative, restoring the mass back to its equilibrium position, back at the very lowest point. So good, we have a restoring torque. We have some constant here, which in this case would be Lmg, but now wait a second. In order to have simple harmonic motion, we have to have the restoring force proportional to the displacement. That's not what we have here. We have our restoring torque not proportional to the angular displacement, but proportional to the sine of the angular displacement. We do not have simple harmonic motion. Although the mass on the pendulum might appear to be simple harmonic, it isn't. And the reason is right here, because this restoring torque is not proportional to the displacement, but it's proportional to the sine of the displacement. So, we do not have simple harmonic motion. However, what does the sine of an angle look like in terms of the angle? What does sine theta look like as a function of theta? Now, let's keep in mind, we're going to look at this in terms of theta being in radians. So, if theta is in radians, how does sine of theta compare to theta? Let's look at that. Okay, so here I have sketched a sine function. So here, this is as a function of theta. The black line here, like this, that is sine of theta. And keep in mind, this is theta in radians. And then the blue line here, this is theta. So theta, as a function of theta, is just a 45-degree line going right through the origin. Now, what I want us to notice is that while these are very different functions, obviously, in here, near the origin, they overlap very closely. They overlap a lot. So what does that mean? Well, for small values of theta, in other words, values of theta close to the origin, small values, sine of theta is approximately the same as theta. So, for small values of theta in radians, the sine of theta is approximately the same as theta. Now, you can actually check this on your calculator. I'll give you some numbers and you can do it on your calculator and check for yourself. and we'll see how this works out. This is called the small angle approximation. The small angle approximation for sine of theta. Okay, let's take a look at some numbers. Okay, so here we've got some angles in degrees and then converted into radians, the sine of the angle, and then the percent difference. So starting out with a large angle, let's say 90 degrees. In radians, that would be about 1.57 radians. The sine of that, the sine of 90 degrees to be precise, is 1.00, and that's a 44% difference. In other words, the percent difference between 1.57 and 1.00. So basically the difference between these divided by their average times 100%. Now, for a smaller angle, let's say 45 degrees, or about 0.785 radians, the sine of that, 0.707, that's about 11% difference. A smaller difference than before, so they're getting closer. A smaller angle, about 20 degrees, 0.349 radians. Now, the sine of 0.349 radians, rather than the sine of 20 degrees, so just taking this as an exact value, is 0.342, and that is only a 2% difference. For a 10-degree angle, or about 1.75 radians, and taking the sine of 0.175 radians, we get 0.174, which is only about a 0.5% difference. A smaller angle, 1 degree, 0.017453 radians. Sine of that is 0.017452, which is only a 0.006% difference. Some very small angle, 0.1 degrees, which is 0.001745329 radians. The sine of that, 0.001745328, or a 0.00006% difference. What we see is that the smaller the angle is, the closer the angle is theta measured in radians to the sine of that angle. So, if we assume that we're going to keep our pendulum oscillating at a small angle, then we can approximate the sine of that angle as the angle itself, theta. And we'll see what that means in just a second. But what do we mean by a small angle? Well, the more accurate you want these results to be, the smaller the angle would have to be. If you don't mind if our results are, say, around 10% off, well, then you could be satisfied with an angle that's around 45 degrees or a little bit less. If you want a 2% precision, well, then you'd need to keep your angle to be less than, say, 20 degrees. If you want 0.5% or, say, a little bit less than 1%, you need to maintain the angle to be less than 10 degrees, etc., etc. So the accuracy that you want or the precision that you want of our results depends on then what angle you'd have to use, how small the angle would have to be. Okay? Great. Let's go back to our diagram. Okay, so what have we just seen? If we keep the angle of our oscillation, in other words, for our pendulum, if we always maintain the angle to be less than 10 degrees, a maximum of 10 degrees oscillation from the vertical, then we can always approximate sine of theta to be about theta, which would only give us about a 0.5% error. Okay, great. Back to the free body diagram. So here's our free body diagram. Again, we've got our mass at the end of our string of length L. Mass M has a weight W equals mg. So what did we find? We found the torque acting on the mass was equal to minus mgl sine theta. As long as we maintain a small angle for our oscillation, we can approximate sine theta by theta. So the torque is then approximately equal to minus mgl theta. So we'll just say the torque is equal to minus mgl theta. And this then looks very much like Hooke's law that we found for the simple harmonic oscillator, a mass on a spring, F equals minus kx, where the torque acts like the force, the restoring torque, rather than a restoring force. The angular displacement theta is acting like the linear displacement x, We've got the minus sign to give us a restoring torque or a restoring force. And then the spring constant is, it looks like it's taking this form of mgl. So the spring constant for the spring is acting like mgl for the pendulum. mgl is like the spring constant that tells us how much the torque restores a displacement theta. Well, for the spring, we found that the angular frequency omega was equal to the square root of k over m. So perhaps then for the pendulum, we can just replace these values. K is mgl. M, the mass for linear motion, corresponds to the moment of inertia. I for rotational motion. So we need to put an I in here, the moment of inertia. The moment of inertia for a point mass that is rotating at a distance L from the origin. Remember, our origin is up here. So for a point mass, the moment of inertia is mr squared. In other words, in this case, ml squared. So we replace the moment of inertia with ml squared. Here, we notice the mass cancels, one of the L's cancel, and we end up with square root of g over L. We have that the angular frequency for a pendulum should be then g over L root. There we go. Well, let's do a little experiment and see if this actually works. Let's stick some numbers in here. Okay, so for a pendulum of length 0.5 meters, half a meter, what would the period be? What is t? Well, we know t is 1 over f, the frequency, and we know the frequency is omega over 2 pi, so 1 over f would be 2 pi over omega. So the period would be 2 pi over omega. Omega is root g over L, so the period is 2 pi root L over g. Well, for a length of L 0.5 meters, we have t as 2 pi root 0.500 meters over 9.80 meters per second squared. Multiply that out, the meters cancel, second squared comes up to the top, square root of second squared is seconds. We end up with 1.42 seconds. Well, let's actually try that. Let's do a little experiment and see if we actually get a period of 1.42 seconds for a pendulum of length half a meter. Okay, I have tried to make a pendulum here as close to 0.5 meters as I can. Hopefully you'll notice that that is very close to half a meter. I've got a stopwatch here, and we're going to measure, rather than just one oscillation, one swing, let's measure 10 swings, and then we can divide by 10 to find the period for one oscillation. Okay, so to measure, let's make sure we have a small angle, so less than 10 degrees. I'm going to count the oscillations from here. So as they go to the right, your right, not mine, I'll start and I'll say 0, 1, 2, so I'll count the oscillations all the way up to 10, and then I will stop my timer. Actually, I've got a timer here. So I'm going to start it here, 0, I'll start the timer there, and then when it passes the center again, that's when I'll stop it. And I'll actually have to use my finger to start the clock and stop the clock. So let's see, I'll use this the pen as the indicator here. Okay, so ready, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, not too bad, I have to say. So my timer gives us a time of 14.25 seconds. 14.25 seconds. 14.25 seconds for 10 swings. Divide that by 10, and we get 1.425 seconds. Now, there's no way that I could have done that accurately to 1/100th of a second. So I would say the fact that we got so close is pretty good. Okay, very, very good. It does then seem to show that this formula works using our analogy with the motion on a spring to find that the period of the pendulum is equal to 2 pi root L over G. Very, very good. Now, if we were to actually start this pendulum and just leave it swinging, okay, and leave it for a long time, obviously if it was maybe attached to something more stable than my hand, and just let this go for a long time, we know that eventually it would slow down and eventually stop. There are always other forces like friction and things like that acting on most oscillators. Simple harmonic oscillators, masses on springs, or pendula, or something like that. So let's take a look at how different amounts of friction, what we'll actually refer to as damping, how damping affects the motion of an oscillator.